So right off the bat, we want to talk about what a proof is, okay? And before I had some other weird, more theoretical definition, but none of that's necessary, right? A proof is nothing but a set of steps that indicate the truth of some statement, okay? So the statement we want to prove is something that we're going to, use a series of implications to show that it's true, okay? And a lot of this mumbo jumbo will make a lot more sense when we look at some concrete examples, okay? So here are some of the types of proofs. We have a direct proof where we essentially just manipulate the information we're given to find our result. We have a proof by a contradiction where we assume that the thing we're trying to prove is false and end up with a contradiction. We use the contraposition, which comes directly from set theory, as we saw last week. Right? That's why we studied the contraposition before. Vacuous proofs, I won't sort of detail exactly what those are just yet. We'll get to them later in the lecture. Proof by cases, where we sort of break up a larger proof into several smaller cases, where we prove each of those individually, and together, since all of those individual cases were true, the larger statement is true. We talk about the idea of counterexamples and how they're not exactly a proof technique, but instead almost like a disproof technique. We can use counterexamples to show that some things are not true, but not to show that they're true. And induction, which is probably the most involved proof technique, we will cover next week. Okay, so our discussion on proofs will start today, go into next week. Sound good? Cool. So let's get right into what a direct proof is. Okay, in a direct proof, we're given some set of information in the problem, and we're sort of asked to determine that to show that some other statement is true. Okay? And as long as each step that we use is valid, our proof is valid. Okay? So towards the end, we'll look at some examples of proofs that are not really proofs because not every step that we made was valid. Okay? So I think the best way to explain what a direct proof is by looking at an example. Okay? Is everyone at the back able to read the question? Sound good? Okay. So we're given that x, y, and z are positive integers. Okay, that's what the math, or like the fancy z with the plus sign means, positive integers. We want to prove that, okay, can anyone tell me what this x vertical bar y means? Divides, good. So can you maybe provide a more mathematical definition?
Y equal b times x.
Good, good. So this means x divides y. Okay, and of course, the next one means x divides z. So we want to show if that x divides y and x divides z, and x divides the sum of y and z. Sound good? So to put this more formally, we'll look at this idea of dividing more in probably 2 weeks from now. How can we write a relationship between y and x if we know that x divides y? I feel like you said it earlier. Do you want to say it a little louder?
I can say y equal a constant multiplied by x.
Good. So if we have x divides y evenly, i.e. that there's no remainder, we can say that y is some integer multiple of x. Is everyone okay with that? So we can say that y is equal to ax. Cool. Now we have that x divides z as well. Can we write another relationship? Yes? Sure, we can say z is equal to bx. Okay? And if we want to be rigorous, we can say a and b are also positive integers. Okay? We want to show that x divides y plus z. What can we do? Well, we can sort of add up our two lines here. We have y plus z is equal to ax plus bx. What can we do here? Common factor the x, right? So we have a plus b times x. And what have we done here? We've shown that the sum of y and z is equal to some constant times x, right? We started off by assuming that x divides y, i.e. that y was some constant times x, that x divides z, i.e. that z was some constant times x, and now we showed that y plus z is some other constant times x. Is that clear? So we took the information we were given, did a little bit of algebraic manipulation, and we are presented relatively straightforward with the result. Okay? We started off that x divides y, x divides z, and now we have that x divides y plus c. Okay? Therefore, x divides y plus c. Any questions with that? So everyone's clear on this notation of the vertical bar in between two numbers. Everyone's clear on all the steps we just made. Cool. So you'll see a lot more examples of direct proofs as you work through the homework. But in terms of explaining the proof technique of direct proof, there's not much else we can do. Okay? So the next proof technique we'll look at is the idea of a proof by contradiction. Okay? And with a proof by contradiction, our task is to prove that some statement S is true. Okay? So, for example, we want to prove that 13 is prime. Well, that's more of a fact, but you get the idea. We want to prove that some statement is true. What we do is we start by assuming that the statement is false. Okay? So we assume S is false. Okay? And then what we do is we make a valid sequence of steps after we assume S is false, and we end up with some sort of contradiction. We'll end up with a line that looks like 0 is equal to 1, or we assume that S was false, and we might end up showing later down the road that S is true. Okay, so we're going to end up with something that just doesn't make sense mathematically. What that something is, we can't really tell in advance. Okay, so that's the issue with a proof by contradiction. You know at the beginning that you're going to do a contradiction by negating the statement you're trying to prove. But the contradiction itself, you don't know what it's going to be until you find it. Is that clear? Like, so for example, if you end up finding that if you assume that S is false, that 0 is equal to 1, you don't know that you're going to find 0 is equal to 1 at the very beginning, right? You're going to have to see that eventually. Okay? Any questions with the idea of a proof by contradiction? Yes?
So let's say if our statement is S equals 1.
Sure.
We're trying to prove that. So the negation of that would be S doesn't equal 1.
Yeah.
However, is a valid negation also like S equals 2 or S equals some other value, or does it have to be S doesn't equal 1?
S doesn't equal 1. So that's a good point. So if our statement is, I don't know, x is equal to 5, the negation of that is x does not equal 5. Okay? Not that x is equal to some other number. It's x is not equal to 5. It could be equal to anything else. Cool. And again, this will be illustrated much easier when we go through an example. Okay? So let's prove that there's no greatest even integer. Okay? So what's the negation of this statement? Yes?
There is some greatest.
Yeah. So let's assume there exists greatest even integer. Let's call it n, okay? Okay? Now what if I create the integer m, which is n plus 2? What can we say about that? What can we say about m? It's even, right? And it's also larger than n. Is that clear? Right? M is even and larger than n. So what's the contradiction here? N is not the greatest even integer, because we found an integer that's even that's greater than n. Therefore, this contradicts n being greatest even int. Therefore, there is no greatest even integer. Any questions with this? So to do a proof by contradiction, we assume the statement we're trying to prove is false, make some valid set of moves, and end up with a contradiction. And here, our contradiction was that we found another even integer that's even larger than the one we assumed was the largest. Is that clear? Sounds good. So now, I want you to work with the people immediately next to you and try and write out the proof that square root of 2 is irrational. Okay, this is like the classic example that we use to show the technique of proof by contradiction. Okay, so I'll give you a couple minutes, try and work through it. I'll give you a hint, it's much more involved than this. It's not that difficult. You might be able to get it within the next couple minutes, but it's far more involved than this first one. Okay, so I'll let you work for a couple minutes. Well, let's walk through it. So we want to prove that square root of 2 is irrational. I already told you we're going to be doing a proof by contradiction. So what are we going to assume?
It's rational.
Assume it's rational, right? And how are the rational numbers defined? Right. We can write any rational number as one integer divided by another. Okay? So I'll say assume square root of 2 is equal to a over b for a, b being in the integers. Okay? What can I do from here? Square both sides probably, right? So I get 2 is equal to a squared over b squared. What can I do next? So that's the thing with these proofs, right? Like, it's not exactly clear what the next step is going to be. You sort of have to do a lot of these to gain the sort of, I don't know, the intuition, that's a good word, to be able to recognize these patterns in questions, because patterns do come up quite a bit, okay? But the first time you see something like this, it might seem sort of foreign. Okay, so what I'll do next is I'll multiply both sides by b squared, okay? So I get a squared is equal to 2b squared. Sound good? Okay. Also, I forgot to mention in the beginning, let's assume a and b are the reduced form of the fraction, right? Like, just like I can write a third as 2 over 6 or 3 over 9, or like, I don't know, a trillion over 3 trillion, let's assume that a and b are the reduced form, okay? So I can say the greatest common divisor between a and b is 1. Sound good? Cool. So now I have a squared is equal to 2b squared. What can I deduce about a squared from here?
Even.
It's even, right? Because it's 2 times some other integer. Is that clear? A squared is even. What does that tell me about a? If some square is even, is it possible for the square root of it to be odd? No. And that's something we'll actually use as an example in a couple slides from now. But for now, let's just take it for granted. If a square of a number is even, the number itself is also even. Okay? So that'll tell us a is even. Okay? How can we represent any even number? And this is an idea that you'll see many, many times from here on out. If some number is even, how can I write it? 2 times k for k being some integer, right? It doesn't necessarily have to be k. So let's say let a be equal to 2k for k is some positive integer, okay? So now I can plug in 2k into my expression for a. So I have a squared is equal to 2b squared. Let me write this a little higher. I have a squared is equal to 2b squared. I can plug in 2k, so I have 2k squared is equal to 2b squared. That means 4k squared is 2b squared. But that means b squared is 2k squared. But now what can I say about b? Or b squared first. We have that b squared is even, right? So it tells us b squared is even, which for now we're assuming that means b is even. Can anyone spot the contradiction? Yes.
You can divide again, I guess.
Right.
Like, yeah, a squared is even, b squared is even, then you can divide both by 2.
Good. We assumed in the beginning that a and b were the reduced, like they made up the reduced form of the fraction that represented the square root of 2, right? We said that a and b have no common factors. But here, we have that a is even and b is even, right? These two facts put together tell us that the GCD of a and b is at least 2. Is that clear? Because they're both even. And so that's a contradiction. Any questions with that? So we started off by assuming a and b were the reduced form of the fraction that made up square root of 2. But then through a series of valid steps, We showed that A has to be even and B has to be even, but that would mean A over B is not the reduced form of the fraction, right? Yes?
Is there some way that you can like easily show that two perfect squares cannot be like, or one perfect square can't be 2 times another perfect square? Like with that, yeah. Would that be a simpler way to?
Prime factors of A.
Yeah, so, yeah, no perfect square can equal to some not square times a square, if that makes sense. Right? Because for it to be a perfect square, it would have to have each factor the same number of times.
Okay.
Right? And so 2 is not a square, so 2 times any square is not going to give you another square.
So can you just do that then? Like when you say A squared equals 2B squared?
Yeah, you could. But this is the more traditional way to do it, but there's nothing wrong with what you're saying. So to repeat that again, we have that 1 prime is never equal to 2 times, or not, 1 square is never equal to 2 times another square. Okay? Because 2 itself is not a square. For this to work, you'd have to have A squared is equal to, I don't know, some 2 other numbers squared. And 2 is not prime, so this doesn't really work. That's a good point. But the traditional way we do this proof is, not that there's anything wrong with the way you just showed, but the traditional way we do is we assume that A and B are the reduced form, but we end up showing that A is even and B is even. That's a contradiction, so therefore square root of 2 is irrational. Any questions? Yes?
By saying that the GCD of A and B can only be 1,
Yeah.
are you like limiting the set of like integers? And are you like allowed to do that?
So, do you agree that if I have, I don't know, A over B, let's use different numbers, P and Q. Okay? I could multiply this by any integer, by any integer k on both the numerator and denominator, and that would give me the same number.
Yeah.
So I'm assuming that there exists some way to write square root of 2 as the quotient of an integer and an integer. Okay? And I'm just assuming one particular realization of it, i.e. the lowest form version of it. Okay? Good question. So we've shown that the square root of 2 is irrational. This is like the most common proof by contradiction that you'll ever see. So make sure you know this one well. Again, it's also in the textbook. Any questions? Cool. I think this is time for attendance. I've been a Lakers fan since July 1st. So the next proof technique we're going to look at are proofs by contraposition. Okay, so remember, the contrapositive of an implication P implies Q looks like not Q implies not P, right? And when we sort of introduced this last week, I asked the question, like, what's the point if it's the same thing? Well, you see the purpose of it now, okay? And so we usually use a proof by contraposition when our required to prove statement, so often you'll see me write RTP, required to prove, is of the form, if this is true, then this is true. Okay? So if we go back to prove that square root of 2 is irrational, it didn't really fit this mold, right? It's just show that it's irrational. There's no if this is true, then this is true. Okay? So not all statements that we're trying to prove have this like form of an implication. Okay? And when our statement does look like an implication, just like the first example did, right? Prove that if x divides y and x divides z, then x divides y plus z. What we want to do is show that the truth value of this implication is true, right? Does everyone remember the fact that implications are nothing but a combination of conjunctions and disjunctions, right? They're propositions on their own. So what we want to do is if our question is asking us to prove something of the form, if P is true, then Q is true, we want to show that the truth value of this proposition is true. Okay? And here we have the truth table for P implies Q and not Q implies not P copied below. But this is something that you should probably be familiar with by now. Okay? So what we'll do is we'll start off by assuming that not Q is true, so Q is false, and we'll show that P has to be false. Okay, and that means the truth value of the statement is true. Okay? What about what's going on down here? Right? The truth value of these implications is also true, right? So that's what's like, this sort of leads us to what's called the vacuous proof, and we'll talk about that if we have time at the end. Okay, but for now, we're not really looking at that. We're sort of focusing on this first line. By showing that when P is true, then Q is true, the truth value of this implication is true. Okay, so a good example is that prove if x cubed is non-negative, then x is non-negative. Okay? So what is our P here? And what is our Q? What does P look like? Yeah, x cubed is non-negative, and non-negative means greater than or equal to 0. I want to show that Q is also, or Q is showing that x is greater than or equal to 0. So what's not Q? X is less than 0, right? We have x is less than 0. Okay, so how can we proceed now? We have x is less than 0. How do we proceed? Yeah.
Then that implies that x cubed is less than.
Yeah, perfect. This proof, there aren't a lot of steps to this one, right? If we're assuming that x is negative, the cube of any negative number is negative, right? You don't really have to draw this graph, but I think it looks something like, I don't know, blah, something like that, right? And if x is negative, clearly x cubed is negative, right? So what this implies that x cubed is also negative. But that's exactly not P. Is that clear? So we wanted to prove something of the form P implies Q. We started off by assuming that not Q, right? So we're assuming that x is not non-negative, i.e. that x is negative. But if x is negative, its cube also has to be negative, right? And so we've shown not P. So since not Q implies not P, P implies Q. And then therefore, if x cubed is greater than or equal to 0, x is greater than or equal to 0. Any questions with this? Cool. A nice little extension to this, though, is whenever we see a proof of the form if P then Q, we don't always have to immediately jump to contraposition. It might, like when you first look at it, you say, okay, we're trying to show that P implies Q, let me immediately start by assuming not Q, right? But just because it's an implication doesn't mean we need to use contraposition. So for example, if we go back to the very first example we did, this was actually an implication, right? If x divides y and x divides z, then x divides y plus z, right? But we didn't jump to contraposition already. Not because we didn't teach it yet, but also because you can do it without using contraposition. So similarly, what we can do is rewrite our implication in terms of conjunctions and disjunctions and do a proof by contradiction. Okay? So what I'll do is give you a couple minutes to discuss amongst the people near you. Think about how we can rewrite x cubed is greater than or equal to 0 implies x is greater than or equal to 0. How we can write that in terms of conjunctions and disjunctions, and what its negation would be. Okay? Remember, when we're trying to show that an implication holds true, right, all we're doing here is showing that this implication has a true value. What we want to do is show that for any combination of x's, this has a true value. Okay? So when we take the negation of it, we're going to assume that this is never true. Okay? So I'll give you a couple minutes to work with the people amongst you, and let's try and come up with a proof by contradiction of this implication. So the statement we're trying to prove is this, okay? This is no different than the statement, the square root of 2 is irrational, right? Just like we could take the negation of that statement, we can also take the negation of this statement. So what does the, okay, first, how can I rewrite this implication in terms of the basic conjunctions, disjunctions, and negations? Any ideas? So remember, P implies Q, what was that logically equivalent to? Not P or Q, right? So not P or Q. So how can I rewrite if x cubed is greater than or equal to 0, that implies x is greater than or equal to 0?
Not x cubed bigger or equal to 0.
Good. So I can say not x cubed is greater than or equal to 0, or x is greater than or equal to 0. Okay? So that's equivalent to me showing that x cubed is less than 0, or x is greater than or equal to 0. So to do a direct proof, what I could do is just show that this statement right here always holds a true value. But instead what I want to do is do this proof by contradiction. Okay? So what I have circled here is our statement S. Okay? So this is no different than the square root of 2 is irrational. This is our statement. We haven't negated it yet. We just rewrote it in terms of the regular conjunctions and disjunctions. Is that clear? So what would the negation of our statement look like? So not S. What would that look like? I'd have to take the negation of the whole thing. Okay? And how do I take the negation of something? This was not explicitly covered, like I never explicitly said this, but it was on the homework last week, and it's in the homework solutions. Okay? We, like in person, we talked about De Morgan's laws for sets, right? We talked about A intersect B, the complement of that is A complement union B complement. And in person, we also talked about the negation of, for all x, I don't know, P of x, is there exists x, not P of x, right? So we talked about these. But we never talked about De Morgan's laws for conjunctions and disjunctions in person. It was on your homework last week, and you'll revisit it in homework this week. Okay? Does anyone know, though? How can I rewrite the statement I have right here? Yes?
Would you distribute the negation and switch the disjunction to a conjunction?
Perfect. Just like when I distributed the complement, you can think of it with an intersection. All the intersections change to unions. And when I did it for the for alls, the all for alls change to there exists. When I do it for conjunctions and disjunctions, when I distribute the negation sign, the conjunctions turn to disjunctions, and the disjunctions turn to conjunctions. Is that clear? Cool. So what would this look like? It would look like, well, not x cubed is less than 0. So that's the same as x cubed is greater than or equal to 0. And what? Not q, right? So x is less than 0. Okay? So right now, this is what I'm assuming. This is the negation of my original statement, right? So this is the negation. Right? So what I have circled here, S, that's our original statement. That's what we're trying to prove. To do a proof by contradiction, we're going to assume not S is true. i.e., we're going to assume that this negation is true. Is that clear? Okay, so we're going to assume that x cubed is greater than or equal to 0, and x is less than 0 holds a true value. But where's the contradiction? Yes?
Cube with any negative number is negative.
Perfect, right? This is a contradiction. This is never true. Because if x is less than 0, then x cubed is less than 0, right? So the contradiction comes from the fact that if q is true, or this is really not q, but if not q is true, then p can't be true either. Is that clear? Yes?
So we're looking at P and not Q?
Yeah,
instead of the
perfect.
current
Yep, perfect. So what we're looking at right now is p, let me erase this line here. Okay, I'll rewrite it. X cubed greater than or equal to 0, and x is less than 0. So this is i.e. p and not q. Good. So if we're trying to show the implication p implies q holds, to do this by contradiction, we could start by assuming that p and not q holds. And we'll arrive at some sort of contradiction. right? If we're assuming that P and not Q holds, we're assuming that x cubed is greater than or equal to 0 and x is less than 0 at the same time. But if x is less than 0, i.e. if not Q is true, then P can't be true. Is that clear? So if x is less than 0, x cubed cannot be greater than or equal to 0. So P and not Q, never true at same time. So that's a contradiction. Okay, so we start by assuming our original statement is not true, so we get to this statement I have here in blue, and then we arrive at a contradiction. We assume that this is true, but then we show that it can't be true. Right? We're assuming the negation is true, but clearly the negation can't be true because x can't be less than 0 and its cube can't be greater than 0 at the same time. So that's our contradiction. Yeah.
Isn't it like kind of like weird, like using proofs for like something like intuitive, like that?
Yeah. So your question is like, what are we really proving here?
Because like yeah, for me it seems like you're just kind of repeating the same like statement.
Okay, that's a good point. The idea with introducing relatively simple examples is just to get a hold of like how we go about doing these proofs. And when we do more examples, we'll do things that are not immediately obvious, if that makes sense. And we'll do some of those today. Is that okay? Cool. Any other questions? Yes?
This is just a trivial question, but is 0 negative, positive, or negative?
Neither. Okay, so 0 is both non-negative and non-positive. Anything else? Yes?
So, I know that for this, now we did it with contradiction.
Yeah.
Prior we did it with
Contraposition, yeah.
And the first one there was also an option. But
Yeah.
Is there like a order, like priority of which one, like which methods,
Like, how do you know which proof technique to use? No, so good question. There will always be more than one way to prove something, okay? Just like even when we were doing the proof that square root of 2 is irrational, we looked at another option, right? We saw that one square can never be equal to 2 times another square. So there's always multiple ways you can do things, and the reason we show all of these techniques is because in some cases it might be easiest to use one way, some it might be easiest to use another way, so that's why we need to see everything. Is that okay? Cool. So remember I mentioned this idea of a vacuous proof, right? So what exactly is a vacuous proof, okay? And I won't spend too much time on this. There will probably be one homework question on it. But let's go back to the slide where we had the proof table, or the truth table for the proposition, or the implication, right? We have P implies Q. This has a true value when P and Q are both true. But it also has a true value whenever P is false. Is that clear? So usually, 99% of the time, the proofs will look at P will be true, like we'll assume that P is true, and then show that Q is true. But if we can show that P is false, then we're done our proof. Because whenever P is false, the implication always holds a true value. Is that clear? So this is weird. We'll rarely use it, but I think it's interesting to bring up. So for example, let's look at this implication. If the earth is flat, then all dogs can fly. That's a true statement, because the earth is not flat, right? Unless you ask Kyrie Irving. I don't know if you know about that joke. But the earth is not flat, right? So it doesn't, like, I could say if the earth is flat, I don't know, 2 is prime. It doesn't matter what I put, whether or not 2 is prime, because the earth is not flat, probably. I don't know, have you seen the whole earth? I haven't. Then it doesn't matter what Q is, right? So if P is false, Q could be anything. P implies Q in this case is always true. Okay? So here's an example of something that's a vacuous proof. Okay? I want to prove that if x squared, or x minus 2, quantity squared, minus 4 is less than 6, then 4 is prime. Okay? Well, let's take a look at this. x minus 2 quantity squared minus 4 is less than or equal to 6, or less than 6, sorry. Minus 6. If I add 4 to both sides, I get x minus 2 quantity squared is less than negative 2. Is that possible? No. Because we know x minus 2 squared is greater than or equal to 0. Therefore, the left-hand side is false. Or we won't say the left-hand side, we'll say P is false, right, if this is P. And this is Q. Therefore, P implies Q is true. Is that clear? We're not proving that 4 is prime, because it's definitely not. All we're saying is that the implication itself is true. And so this is a good exercise in getting you to think about implications as being propositions themselves that just happen to have a truth value. Is that clear? Normally when we do implications, 99% of the time, as I said, we'll be trying to show, given some set of true information, we're going to show that this other set of true information holds. I.e., we're going to do true implies true most of the time. But this is an example showing that even though P is false, this implication itself holds true. Any questions with that? So this is not a proof that 4 is prime. I hope that's clear. Any questions? Yes?
What's that symbol you're doing to denote like what 4 is?
Yeah, oh, that's a good point. The 3 triangle, or the triangle with dots, means therefore. And so you'll see that a lot in proofs. And notice when we've done every single proof, I wrote a sentence at the end saying therefore whatever we were trying to show holds. Okay? In this class we're not going to grade you on that, but in future classes, like CS70 maybe, that's something they're going to look at. And it's just good practice. Okay? Yes?
So when you say P implies Q
Yeah.
is true, what does that mean in the context of the original problem?
All it means is that this statement, or like a good way to think of it, is the statement, if the earth is flat, then dogs can fly. The earth is not flat and dogs can't fly. But the statement, if the earth is flat, then dogs can fly, is a true statement. Okay? And the way I like looking at it is, if P is false, then the regular laws of our universe don't really hold. So it doesn't matter what Q is, whether or not it's true or false. Sure, it's possible if the laws of our universe don't work. Right? Like, if the earth is flat, then obviously something's fucked up. Dogs can fly. I gotta edit that out of the webcast. But, yeah, any questions?
Yeah, so previously you had the lecture with implications that had one error and then if and only if.
Yeah.
So what would a sentence look like for if and only if?
Okay, that's a good question. So, this is a bad example to do it on because it's just not true. But how about here? An if and only if would look like x cubed is non-negative if and only if x is non-negative. And this is actually something that you'll also explore in the homework. Okay? Remember, if and only if is an implication in both directions. We show that if A, if and only if B is true, then A implies B and B implies A. Is that okay? So in order to show some statement that includes an if and only if, we'll have to show the implication both ways. Otherwise, it's not a complete proof. Okay? That's a good point, and you'll see a lot more of this. But to show x cubed is non-negative if and only if x is non-negative, you'd have to show the direction one way and the opposite way. Good point. Cool. Any other questions regarding vacuous proofs? Cool. So the next proof technique we're going to look at is more of a combination of multiple proof techniques. Okay? So in a proof by cases, we have some statement that can be broken up into multiple different cases. Okay? And I can't really put it any better than that other than by showing an example. Okay? And what we will do is break, suppose we want to show that something is true for all x. We can break x up into multiple cases and show that it's true for each case. And if it's true for each case, then it must be true in general. Is that clear? That's the general premise of it. Okay? So here we want to prove that the cube of any integer is either a multiple of 9, one more than a multiple of 9, or one less than a multiple of 9. Okay, so this is a proof that we're going to do by cases. But first, I want you to work again with the people near you and try and determine what are I'll tell you right now, there are 3 cases that we're going to break X up into. What are those 3 cases? And try and do the proof for each of those cases. Okay, so I'll give you a couple minutes to work on that. Okay, cool. Let's come back together. Okay, so we want to prove that the cube of any integer is either a multiple of 9, 1 greater than a multiple of 9, or 1 less than a multiple of 9. So I told you that we have to break up into X into 3 cases. What were those 3 cases? Any ideas? I know it seems like you know. So someone else maybe. Yes? So you could use modular arithmetic, but we'll save that for when we talk about that in this class, maybe 2 weeks from now. Okay? Any other ideas? So for proofs like this, it's going to seem random, like pretty arbitrary, where I come up with these 3 cases for X from, okay? And the way you'll gain the intuition for doing this sort of thing is by practice, okay? So you'll see it now, and if you see a similar question, I don't know, maybe on the midterm for this class, maybe in CS70, I don't know, you'll have seen this before, and you'll sort of know what to do with it. Okay, so let's go from there. So the 3 cases I'm going to break up X into is a multiple of 3, 1 greater than a multiple of 3, or 1 less than a multiple of 3. Okay? Is everyone okay with the fact that I could equivalently write 3k plus 2 or 3k minus 1? Being 1 less than a multiple of 3 is the same as being 2 greater than the next smallest multiple of 3. Is that clear? Right, like if I write, I don't know, 6, 7, 8, 9, 10, 8 is 1 less than 9, but it's also 2 greater than 6. Okay, so those 2 things are equivalent. And so what am I going to do? I'm going to cube each of these 3 separate x's and show that the statement holds for each of them. Okay? Let's go about doing it. So the first one, x cubed is 3k cubed, which is 27k cubed, which is 9 times some integer. Does that hold? Yes. Question?
For the second statement,
Yeah.
should that be 3k plus 2?
Okay, so that's what I just said. So you could either write it as 3k plus 2, or you could write it as 3k minus 1. The k's are not the same in these cases. Okay, k is some general arbitrary integer. It's not necessarily, like, we're not assigning it a value. We're just saying that x can be written as 3 times k for something. Okay? So writing it as 3k minus 1 is the exact same as writing it as 3k plus 2. Yes?
How did you get 3k in the first place?
Like, how did I come up with this?
Yeah.
It's because I know how to do it. And so, okay, that's not a great answer. But as I was saying, there's a pattern that sort of occurs when you're doing these proof problems, and this is something that you'll sort of get used to. And so you've seen it now. When you see it in the future, you'll sort of pick up on the pattern.
Okay. Well, like, why it's not 4k or 5k or 2k?
So that's a good question, because we know it's going to have to deal with 9, right? And if you cube 2, it's 8. That's not really 9. That's not a multiple of 9. But if you cube 3, you get 27, and that is a multiple of 9. Is that clear?
Or is it because multiple of 9 implies it's multiple of 3?
If it's not quite. So what we want to show is that each of these 3 cases for x can either be written as 9 times some integer, 9 times some integer plus 1, or 9 times some integer minus 1. Is that clear?
Yeah.
And if we let x be some multiple of 3 and we cube it, we know a 27 is going to be involved somehow, but 27 is a multiple of 9. So that's sort of where it comes from. Is that okay? And yeah, I agree that it seems like I sort of pulled this out of nowhere, but the more problems you do, the more common this pattern will sort of become. Okay? Cool. I won't do it for both cases 2 and 3. It's more or less the same thing. So if I cube x here, I get 3k plus 1 cubed. What does that give me? 27k cubed plus 9 I should know this. We teach this in this class. 3 times, I believe it's 27k, plus 9k plus 1. Okay? It might be slightly off, but for the purposes of this proof, it doesn't really change anything. Okay? But we can write this as 9. Was it 27? Yeah, good point, good point. It doesn't really change anything. They're all either 9s or 27s. Okay. But we can factor out the 9 from the first 3 terms. And so now we have it in the form of 9 times some integer plus 1. Okay? You'll often see me writing box and triangle. That's just an abstraction, 60 knowledge, for like some integer. Okay? And to show that some integer is 1 greater than a multiple of 9, I show that it's 9 times some other integer plus 1. Is that clear? So I've shown that in the case that x is exactly a multiple of 3, the proposition holds. I show that if it's 1 greater than a multiple of 3, the proposition holds. And if I do the same thing for x cubed being 3k minus 1, it's actually very similar. Okay? And might as well write it out. The numbers are the same as before, but the signs alternate. And this is like the way you do this is something called the binomial theorem, which we'll study very extensively probably towards the end of this class. There are a lot of cool things you can do with it. 9k minus 1, but that's the same as 9 times some integer minus 1. So the proposition holds for all 3 of these separate cases for x. Yes?
When you're formulating the cases, should you consider, should you make the cases so that they cover the,
So I get your question. It happens to be the case that in case 1, I showed that it was exactly a multiple of 9. In case 2, I happen to show that it's 1 more than a multiple of 9. And in case 3, I happen to show that it's 1 less than a multiple of 9. Does it always have to be like that? Is that your question?
not really. I'm saying that for the cases you came up with,
Yeah.
you should show that this 3 kind of cases covers any integer.
Okay, yeah, sorry. That's a good point that I should have mentioned. Okay? Any integer, do you agree with me that any integer is either a multiple of 3, 1 greater than a multiple of 3, or 2 greater than a multiple of 3? Is that clear? Right? And that's exactly what we've shown here. These cover all integers. Is that clear? So I sort of said it earlier, didn't emphasize it, but within these 3 cases, we cover all possible cases for integers. Is that clear? Okay? And so for each individual case, we show that the proposition holds true, and therefore the proposition holds true for all integers. Sound good? Yes?
Would a different number other than 3 still this?
Could I have done it with a number other than 3?
Yeah, let's say 9 or a different.
I believe if you did it, like this is not for sure, but I believe if you did it with any multiple of 3, it also would have worked. Okay? Because the first term is that number cubed, and if it has a multiple of 3 in it, it will have a multiple of 27 in it, so we can do the same thing. The second one will be whatever number we choose squared, and if that has a multiple of 3, it's squared will have a cubed will have, you get what I mean, right? Like if we use any multiple of 3, this should also work, I believe. Good question. Any other ideas? Cool. So one of the last things I want to talk about is this idea of a proof by counterexample. But it's not a proof technique, okay? So you can't prove something by giving a counterexample. Instead, what we use a counterexample for is to show that something is not true. Is that clear? So if someone gives us a statement, prove or disprove the following statement, and we find just one example of it not working, well then we've disproven it, right? Because it's not true for all possible numbers, or for the sample space that they're given, right? You can't prove that something does hold by giving one example, because you have to show it holds for all possible numbers, or all possible elements in the set that you're talking about. But to show that something does not hold, you can give just one counterexample. Is that clear? Okay. So as an example, prove or disprove the fact that all Pythagorean triplets are of the form 3k, 4k, 5k. It's not true because 8 squared plus 15 squared is equal to 17 squared. And by Pythagorean triplet, I mean a comma b comma c satisfies a squared plus b squared is c squared, okay? It's clearly not true because 8, 15, 17 is a Pythagorean triplet, but it's not of the form 3k comma 4k comma 5. Is that clear? So again, this is not a proof by counterexample, but I use the counterexample to show that it doesn't hold. Any questions with this? Yes?
So if we actually want to prove that all Pythagorean triplets are not of the form 3k, 4k, 5k, then could we just basically write a proof, an actual like formal proof with just one counterexample?
So if our proposition was prove that not all Pythagorean triplets are this, then yeah, you could show just one example, and therefore not all of them fit this format, because I showed one that doesn't.
And that would be a rigorous proof?
Yeah, because so rarely will we have the problem of prove that not this is true. Okay, but in the event that we do, that would suffice, because all we're asked to show is that there's some number or some ordered pair or some whatever that doesn't hold. Okay, and that's sufficient to prove our statement. So that's a good point. Like a lot of these proof techniques, we're sort of just introducing the idea, but for each question you sort of want to determine which technique works best. Okay, and you have to make sure that you're being rigorous with each one. So showing an example is not a proof technique in general. Showing a counterexample is a way to disprove something. Sound good? Cool. Lastly, what I want to do is take a look at some proofs that just don't make sense. Okay? And I believe this is an important skill to also have because the more you're able to decipher other proofs that may or may not make sense, the more knowledge you will be in writing your own proofs. Okay? So some common mistakes that are often made in proofs, the biggest one is probably assuming that the statement you want to prove holds true. Okay, so watch this. Let's say I'm required to prove 1 is equal to 2. Okay? Let's assume 1 is equal to 2. I multiply both sides by 0. I have 0 times 1 is equal to 0 times 2. I get 0 is equal to 0. Because that's true, 1 should be equal to 2. Obviously that's not true, right? Because I assumed what I was trying to prove. Okay? So cross that out. Not good. Another common mistake that happens, and we'll look at an example of this on the next slide, is dividing by something that could be 0. Okay? Even if there's a possibility that some number is equal to 0, you can't divide by it. Okay? You have to consider these cases separately. And there are a whole multitude of other things that often occur. They're not just mistakes that people make in doing proofs, but just mistakes in algebra in general. Like, I don't know, when you have an inequality, you forget to multiply by -1. Or so you forget to flip the sign of the inequality when you multiply by -1. Or you use an example to show one case is true, but there are multiple cases. Okay, these are all different things that are not rigorous and just not proof techniques. Okay? And so you'll have to be on the eye for some of these. And again, you'll have practice in the homework of reading some proofs and determining why they're not true. Okay, I'll give you a hint right now. We're going to have a question that asks you to read a proof, and it's going to look like it's a proof by contraposition. But instead, what they will have done is assume Q and show P. But proof by converse is not a real thing, right? Because the converse of a statement and a statement itself are not the same, right? We can do a proof by contraposition, right? Because not Q implies not P is the same as P implies Q. But Q implies P is not the same as P implies Q. Okay, so that's something to be on the lookout. This idea of a proof by converse is not a real thing. Yeah?
So it says using an example as a proof for a statement applies to multiple of the cases, but
Yeah.
why would that be bad if you, I guess, take care of multiple cases with one example?
Yeah, so I guess this line doesn't make a whole lot of sense. Let me think about that and get back to you, if that's okay. Cool. Any other issues with this? Okay. So let's look at this beautiful proof that we have. Okay? So we're going to prove 1 is equal to 2. And at first, there might not look like anything's wrong. Okay, what are we going to do? Let's let x be equal to y. We're assuming these are some numbers. Then x squared is equal to xy. Yeah, that makes sense to me. Nothing wrong with that. If I subtract y squared from both sides, also seems legit. If I factor the left-hand side by difference of squares, I get x plus y times x minus y. And I can common factor out a y from the right side. So I get y times x minus y. Okay. Let's divide both sides by x minus y. Why not? Okay. So you get x plus y is equal to y. Let me not write a check mark there. But since x is equal to y, instead of writing x plus y, I could just write 2y. Okay, so now I'm at this stage, 2y is equal to y. And then I divide by y, and I'm left with 2 is equal to 1. So what are some of the issues with this? Because this is I don't know what you call this. It's definitely not math, but I don't know what it is. Honestly, where I found this was from like this Facebook group. It was like mathematical edgy memes or something. And now you'll be able to look at these memes. Okay. What are some of the problems with this? Yes?
You can't divide by x minus 1.
Yeah. X minus y is 0. Can't divide by it. Why is it 0? Well, because we said x is equal to y. Okay? What's another problem? Because that's not the only one. Yes?
You have to factor out why you can just divide by 1.
Yeah, right here. You're supposed to isolate for y on one side of the equation. You can't just divide by y, because what if y is 0? Have to rearrange for y. Can't divide by it. So obviously this is a relatively silly example, but you can see how this could be extended to something a lot more complicated where the mistakes you make are not immediately evident. Is that clear? So you always want to be on the lookout and make sure every single step you make in your proof is valid. Any questions with that? Cool. So sort of to wrap this up, the ideas of a direct proof, a proof by contradiction, and a proof by contraposition will probably be the ones you see the most common of what we've covered. Okay? And you'll get a lot more practice in a lot of these ideas in this week's homework. You'll have practice doing questions both with the contradiction and contraposition, sort of like we saw in lecture today. You'll be introduced to this idea of if and only if, and how you have to prove an implication in both directions. And next week, we'll start talking about this idea of mathematical induction, which allows us to prove that a property is true for all natural numbers. Okay? And you can start reading the textbook for that if you're interested. It's not fully complete yet, but that's sort of what we'll be talking about next week. The homework will be released later tonight or early tomorrow, same due date on Monday. We have office hours tomorrow if you're interested. Thank you.